In this video, we will familiarize ourselves with the conformational isomers of cyclohexane, covering equatorial versus axial positions in the chair conformation, chair flips, and destabilizing gauche and 1,3 diaxial interactions in substituted cyclohexanes. In the last video, we left off our discussion on the conformational isomers of cyclopentane. Now we will move on to the final important ring for this course, the six-membered ring cyclohexane. As we discussed last time, the better a ring can alleviate torsional strain and maintain bond angles closest to the ideal 109.5 degrees, the less ring strain it has, making it more stable. This trend explains why cyclopentane is much more stable than cyclopropane and cyclobutane. A hexagon has interior angles of 120 degrees, which is farther from the ideal bond angle of 109.5 degrees compared to cyclopentane's 108 degrees. Based on this trend, we might predict that cyclopentane would be the more stable ring structure. However, this isn't always the case, as cyclohexane can adopt a conformation that completely alleviates all ring strain. In this conformation, there is no angle strain and minimal torsional strain due to the staggered carbon-carbon bonds. This conformation is one of the few conformations cyclohexane can adopt. Let's briefly explore these conformations and order them from highest to lowest energy. The first conformation is the flat conformation of cyclohexane. This conformation has the highest energy due to significant angle strain from the 120-degree bond angles and high torsional strain from the eclipsed hydrogens. If we grab carbon 1 of the ring and pull it up to adopt the ideal bond angle of 109.5 degrees, we can transition from the flat conformation to the half-chair conformation. This reduces the number of eclipsing interactions and non-ideal bond angles, decreasing the conformation's energy compared to the flat conformation. Next, if we pull up the carbon 4, we can move from the half-chair conformation to the boat conformation. This conformation minimizes angle strain and relieves some torsional strain. However, the hydrogens labeled in red experience van der Waals strain due to their close proximity and overlapping van der Waals radii. The boat conformation is quite flexible, allowing it to twist at the bottom, creating the twist boat conformation, which eliminates the torsional strain experienced by the hydrogens labeled in red by offsetting them from their eclipsed position. Finally, returning to the half chair, if we pull down carbon 4 so that it also adopts the ideal bond angle of 109.5 degrees, we achieve the chair conformation. The chair conformation of cyclohexane is a perfectly unstrained molecule with an energy of 0 kcals per mole. For the purposes of this course, we will focus primarily on the chair conformation of cyclohexane. You will most likely not be responsible for knowing much about the boat or half-chair conformations. Let's take a closer look at the chair conformation of cyclohexane and explore its unique structure, starting with how we draw a chair. There are two common ways to draw the chair conformer of cyclohexane. In the first method, we start by drawing two slightly offset parallel lines like so. Next, we draw another pair of parallel lines extending from the ends of the first pair and connect them with a third set of parallel lines. In the second method, we begin with a blank sawhorse projection. From the two lines on the right side of the projection, we draw two lines each parallel to the line opposite them, like this. Finally, we close off the chair by drawing a third line parallel to the center line of the sawhorse projection. This method is particularly useful because it allows for the easy addition of substituents. Let's go back to observing the chair in 3D. Observing the chair conformation from this angle, we can see that each of the CC bonds is in a staggered conformation. We can also depict this using a Newman projection for better visualization. Now let's rotate the molecule to its side and observe it from the perspective typically used to draw the chair conformation. From this viewpoint, we can see bonds to groups pointing straight up or down, and others angled up or down, pointing to the side. The vertical groups are said to be in the axial position, while the groups pointing off to the sides are in the equatorial position. Additionally, we refer to these groups as up or down based on their position. Here, I've labeled all of the groups in the chair conformation as axial or equatorial and as up or down. Now let's discuss another unique property of cyclohexane, ring flips. Earlier, we achieved the chair conformation by starting from a half chair, raising carbon 1 to adopt the ideal bond angle of 109.5 degrees, and then lowering carbon 4 to match the ideal angle as well. Interestingly, however, we can also achieve a chair conformation by starting with a half chair where carbon 4 is pulled up to the ideal bond angle and then pulling down carbon 1 to match. Cyclohexane can switch between its two most stable chair conformations through a process known as a ring flip or chair flip. During a chair flip, all axial groups become equatorial and all equatorial groups become axial. However, the groups that were pointing up or down remain pointing up or down in the flipped conformation. The energetic cost of a chair flip is approximately 10 kcals per mole, making the energetic barrier small enough to allow the two conformations to interconvert at room temperature. This property has interesting consequences when it comes to mono, di, and multi-substituted cyclohexanes. Let's start off with a mono-substituted cyclohexane, methyl cyclohexane. Under standard conditions at equilibrium, methyl cyclohexane exists 95% of the time with the methyl group in the equatorial position and 5% of the time with the methyl group in the axial position. We just learned that cyclohexane can readily convert between the two chair conformations with relatively low energetic cost. So, what causes this extreme bias for the methyl group to be in the equatorial position? This extreme bias would suggest that the equatorial conformation is lower in energy than the axial conformation, and that is exactly right. Looking at a Newman projection of these two chair conformations, we notice that in the conformation where the methyl group is equatorial, there are no destabilizing interactions contributing to torsional strain, maintaining the chair conformation's relatively low energy. However, in a Newman projection where the methyl group is axial, there are two destabilizing gauche interactions between the methyl group and carbons 3 and 5 in the ring. Here's an alternative view to help you better visualize these interactions. This energetic consequence is even greater in di and multi-substituted cyclohexane rings. For example, in cis-1,3 dimethyl cyclohexane, there is a significant difference between the relative energies of the conformation where the methyl groups are axial and the conformation where they are equatorial. In addition to increased gauche interactions, the two methyl groups in the axial positions experience a specific type of steric clash known as a 1,3 diaxial interaction. This interaction, also referred to as a 1,3 eclipsing interaction, increases torsional strain due to the close proximity of the axial substituents. The final topic we'll cover is how to draw substituted chair conformations starting from a flattened representation of the cyclohexane ring. Let's take a look at trans 1,3 dimethyl cyclohexane represented as a flattened ring. In this depiction, the methyl substituents on carbons 1 and 3 are positioned such that one points towards us, represented by a wedge, and the other points away from us, represented by a dash. A general rule for converting these flattened depictions into chair conformations is that a wedge substituent will be positioned up while a dashed substituent will be positioned down. Here is this molecule drawn in one chair conformation with one substituent in the equatorial position and the other in the axial position, and in the ring-flipped conformation where the positions of the substituents switch. The equatorial becomes axial and the axial becomes equatorial. Notice that in both chair conformations, the wedged substituent remains up and the dashed substituent remains down, maintaining their original orientations. As always, let's do some practice. Given below are two stereoisomers of glucose, alpha-D-glucose and beta-D-glucose. In aqueous solution, these stereoisomers rapidly interconvert and reach an equilibrium. Predict which stereoisomer is more prevalent at equilibrium and explain why. Feel free to pause the video and try this problem on your own first. Although glucose isn't exactly like cyclohexane and cannot undergo ring flips, the principle that the lower energy form will predominate at equilibrium still applies. To determine which stereoisomer of glucose is lower in energy, we can examine the destabilizing interactions in each isomer. In alpha D glucose, the hydroxyl group attached to the anomeric carbon is in the axial position, leading to 1,3 diaxial interactions with other axial groups in the ring. These destabilizing interactions are absent in beta D glucose, where the hydroxyl group is in the equatorial position. Therefore, we can predict that beta D glucose is the species that predominates at equilibrium. Let's move on to the next question. Rose oxide is an organic compound known for its pleasant floral scent, commonly found in the essential oils of roses. It is widely used in perfumery and flavoring due to its distinctive, sweet, and floral aroma. Given the stereoisomer of rose oxide below, redraw this stereoisomer in the chair conformation. Feel free to pause the video and try this problem on your own first. In this stereoisomer of rose oxide, the hydrogen adjacent to the alkynyl substituent at the 2 position is in a wedged position, indicating it is coming out of the plane towards us, while the methyl group at the 4 position, opposite the oxygen in the ring, is in a dashed position, indicating it is going behind the plane, away from us. Recall that substituents on a wedge are considered to be in the up position, while those on a dash are in the down position. In this stereoisomer of rose oxide, this configuration places the hydrogen adjacent to the alkenyl group in the equatorial up position and the alkenyl group in the axial down position. The methyl group, being dashed, is also positioned axial down. Let's move on to the next question. The change in free energy corresponding to an increase of 1 order of magnitude, tenfold increase in the equilibrium constant, is approximately 1.36 kcals per mole. For the stereoisomers of disubstituted cyclohexanes shown below, compare the relative stabilities of cis 1,2-dimethylcyclohexane and trans 1,2-dimethylcyclohexane conformers. Explain why the energy difference between the cis and trans conformers leads to a different equilibrium constant and how this difference impacts the conformational isomerism. Feel free to pause the video and try this problem on your own first. Let's begin by calculating the relative energies of each stereoisomer by identifying any destabilizing interactions in both ring conformations. Note that in the chair flip conformations, the ring is slightly rotated to provide better visibility of the substituents. In the cis isomer, both chair conformations have 3 C-C-C-C gauche interactions, meaning that interchanging between these 2 chair conformations offers no energetic advantage. As a result, the equilibrium constant K for the interconversion between these 2 chair conformations is 1, and the delta G of the reaction is 0. In the trans isomer, performing a chair flip from the conformation on the left to the one on the right increases the number of destabilizing gauche interactions in the ring by 3, going from 1 C-C-C-C gauche interaction on the structure where both methyl groups are equatorial to 4 C-C-C-C gauche interactions on the structure where both methyl groups are axial. As a result, we can conclude that the equilibrium constant K for this interconversion between the 2 chair conformations is less than 1. We can calculate the delta G for this reaction by multiplying the difference in the number of gauche interactions 3 by the energy associated with each C-C-C-C gauche interaction, 0.9 kcals per mole, resulting in a value of plus 2.7 kcals per mole. To determine how much less than 1 the equilibrium constant is, we can use the value provided in the problem, 1.36 kcals per mole, which corresponds to the change in free energy for an increase of 1 order of magnitude in the equilibrium constant. By dividing 2.7 kcals per mole by 1.36 kcals per mole, we find that the equilibrium constant is approximately 2 orders of magnitude in favor of the structure on the left. Therefore, the actual value of the equilibrium constant is approximately 10 to the minus 2. As always, thank you for watching, and I'll see you next time.